All right, I'm just firing up the YouTube stream right now. I was the first one in the audio chat today. I'm getting my game. I'm getting back on my game. This is all about milestones right now, you know? It's like can I find a little milestone? I'm getting back. Okay, how are we doing here? All right, there's our link. Boom. Okay. 11:30. I know that there's like a bunch of people that are like, yeah, Dr. K, man, he's like on drugs or something, and heavy narcotics for pain management, and he's going to be running a little late always, and that's kind of true, has been anyway. But I'm feeling it today. I'm actually feeling it, feeling my oats. So, and I was the first one in the voice channel. Oh yeah. So I'm ready to rock and roll. I'm ready to go. So let me see. We got, all right, streaming is going, cranking. Yep. Um, all right. You guys are there any questions? Um, any, housekeeping, any logistical, anything that anybody's, you know, not getting or not understanding or struggling with or whatever. Um, One other thing, by the way, I'm going to join. I am feeling better. Every day I'm actually feeling better on this post-surgery crap. Nerve pain is still a thing, but I think that is even maybe getting better. Might be getting better. Not sure. Today I'm going over to Cabela's. I live near Cabela's. I'm going to go over to Cabela's and buy a cane for walking, for my walks, because I'm in old man zone. I need a cane for my walking just because of the bum leg in this post-surgery nerve pain recovery zone. So that'll be cool. I'm going to graduate my walker to a cane. So um, I don't know what to say, my friends. But anyway, please remember, keep playing bingo, keep grabbing the homework, be on the homeworks. Uh, some of these concepts they just kind of blow the mind just a little bit. This course, 2810, man, it's a lot of new paradigms. If you haven't seen it before, for some of you that have, you're like, no, this is not hard, not really. Man, if you haven't seen it before, right? I mean, and this is the very first time you're seeing it, and we're going to hit you with number systems and binary arithmetic and bitwise operations and logical, and then we're going to get over to these circuits and transistors, and eventually to, architecture and assembly language. This class has a tremendously high level of just new things that we're throwing at you, and you got to have them, and they're really important to the whole field of computer science, and throughout your career. But it can be a little bit daunting. That's all I'm saying. So, just as a reminder, again, this is my little motivational speech. As a reminder and as a motivator, I don't know. I'm not muted, Braden. Others can hear me, right?
Yeah, you're good.
That's just, sorry, Braden, man. That's just you. Um, but uh, the only way to handle all these new concepts is to dive in. They're not just going to wash over you like a shower, get in the shower, run them over your body, and then get out and you got it. There are topics that are like that, either because the topic's just super easy or maybe it just really resonates for you. But this is one of those topics that experience shows that it just takes immersion. You have to go to it and hit it. And, Dr. K's theory of learning. Did I ever share with you Dr. K's theory of learning? I'm going to now. And then we're going to go back to this thing. We're going to talk about memory. We're going to make some memories. Dr. K's theory of learning is really, really simple. Number one, Braden, you may have to restart Discord. I'm not sure. That would be my biggest recommendation. Number one, you have to basically, I put it this way, I usually refer to it as enjoy doing it badly. You know, if you can find a way to enjoy it, that's ideal. Even if you can't enjoy it, you got to find a way to motivate yourself to do it and to be okay doing it badly. Just that's it. But you just keep doing it even though you're bad at it. Because everybody starts everything that they're brand new at bad at it. By definition, you know, you can't expect to just, oh, I'm going to try to play the piano today. Oh, look, Chopin. No, no, your hands are so uncoordinated and spastic, they won't even cooperate. You know, I spent, you know how long I spent, I haven't done this in a while. Do you know how long I spent just doing this, trying to figure out how to twirl the drumsticks in my fingers? You know what I mean? You know how, I mean, and that's not great. That's still not great, okay? But it's not crazy bad. You know how many times I've gouged my eyes out flinging these things or doing it and uh, have them just fly out of my hands, and you look like a doof, right? You're never good at it to start. So you got to find a way to enjoy doing it badly. That's step number one. And step number two is trust your brain. Trust your brain. Your brain wants to solve puzzles. Your brain loves to solve puzzles. When you start doing a thing like that, trying to twirl the drumsticks, for example, um, your brain actually knows what you're trying to do there and wants to figure it out. So it'll work on it. By the way, I actually haven't done that attempt since pre-surgery, so I haven't actually done this in more than a month, and I've got at least some chops on the spin. It also has to do with the angle. You know what I mean? You got to get the angle just right so it looks more impressive to the audience. But your brain is working on it even when you're not, as long as you do it frequently. And frequency is more important than duration. If I could spend 8 hours on like Sunday or Saturday every week, and that's my 28:10 time, it's better if you could spend an hour every day so that your brain is reminded and your brain will work on it. And that's it. That's it. Enjoy doing it badly. Trust your brain. But it is a function of time and effort spent in it, reviewing it and doing it and going through it and going through it and trying to figure it out in your mind, okay? It can be done. Anybody can pass this class. I really do believe that. But not if you bail. Not if you bail. Because if you bail, what
You
happens?
feel
You fail. That is the only way to fail this class is to bail. And if you bail, I can't help you. There's nothing I can do. There's nothing to work with. You do it, and then you've got me, you got Walter, you got Zach, and we are just ready. I'm coming back online, okay? So I'll be better at my office hours and being available at other times. Okay, that's my speech. I think it's a good speech. But I just want to encourage you because I'm sensing in some of you an eagerness, but there's still like it's just like, ah. And then when you do something like that, you know what I mean? And it's like, no, and you blow your circuits a little bit. Don't blow the circuits. Okay, stay with me. Stay with me. Okay. I hope that you appreciate the speech. And by the way, spring break, this is it, Thursday, and then we're not back till the Tuesday after spring break. It is a really good time to catch up. Everybody, please, I beg you, I want you to succeed. In my perfect world, everybody that takes this class gets an A. In my perfect world, there's no curve. The bell curve, I have some opinions about this. Okay. The bell curve is a travesty, in my opinion, because it takes something which is descriptive and makes it prescriptive. Right? It is descriptive in the sense that, yeah, it does tend to fall out that way. But then imposing that denies the fact that the distribution doesn't always match that. It's bad. It's statistical malpractice, in my opinion, of the worst order to apply a bell curve and say so many people have to fail or whatever. Enough speeching. Enough speeching. Um, let's see. I need a character shift. So we're gonna go Colonel Sanders for just a little bit. That's probably good. Okay, that's just a reset. Are you ready for memory? Yes, you are. We talked about this just at the very end of Tuesday. The very end of Tuesday, I was showing you this thing, and I was saying, look, don't freak out. It's a 12-bit memory. There are 4 bytes. That's a byte. These 3 bits right here, that's a byte. We could make it an 8-bit byte. We just have to extend the picture. You know what I mean? You have to just keep repeating the pattern that you see here. Notice that right in here is your RS latch. And if you go back like we were doing, back up to here, if we go all the way back, you'll see that's what this is, okay? We've got the address lines. Okay, so that's a byte. This is address 00, okay? That's the byte at address 0. That's 01, 10, 11. And notice that we've got this decoder right here. Now, and by the way, I apologize for the pink, not my color selection. This was a graphic that came from the publisher, of our book. And sadly, it came with pink box, whatever, like, pre-made. I didn't want it. Okay. This is a decoder. It has to make one of 4 selections, right? Remember, it can be 0, 1, 2, or 3. This decoder takes these 2 lines, 2 bits, because with 2 lines and 2 bits, I can select 4 things. They can both be off, right? Or they can, one of them is on, or they're both on. And notice, if you can see this again, I apologize for I think the resolution's okay from what you can see, but notice that right there is the 2 NOT gates right in front of the AND. So when this guy's 0, 0, what's going to happen? That line is going to be on, and all of these are going to be off. When it is 1, 0, this one will be on. When it's 0, 1, that one will be on. And when it's 1, 1, then that last guy's going to be on. Okay? So literally, as that address, those 2 address lines move from 0, 0, 0, 1, 1, 0, 1, 1, whichever one they select, that line is on and all the others are off. That becomes really, really key. Okay. This is what we use when we're writing data into memory. These are the data lines coming in. And that is when we're reading from memory. So it's called data as well, but this is when we're reading from memory on the bottom end, okay? So here's what we're gonna do. We're gonna do it. We're gonna walk through it. And I'm looking just real quick. Okay, another. Oh, and by the way, before I forget, Eddie dropped a bunch of resources. Thank you, Eddie. Great stuff. And by the way, I have read Claude Shannon's famous paper. It's pretty dense. It's pretty difficult.
It's so long.
And it is long. Yeah, I actually first acquired it in book form as a small book. It's a pretty long paper. But yeah, if anybody's interested, hit those links. So really, Eddie, thank you so much for dropping that for everybody. And it's one of the things that I try to encourage here is kind of the group ethic where we help each other. It's great for you guys to help each other, whether it's on the general chat or jumping on DM, as long as you're not taking somebody else's work and passing it off as your own, it's not cheating to help somebody understand material and to walk through stuff. But I really love it when you help each other. Okay, here's our quest. Here's the values in memory. Okay, byte 0, 0 has 0, 1, 1. Right? These are just, it doesn't matter. These are just random. And we are going to read the value of the 3-bit byte at memory location 1, 0. So 0, 0, 0, 1, 1, 0. Now I want you to notice the notation that I've been using to this point with like thick red versus thin red, where thin red means it's a zero, right? The line is off, and thick red means that the line is on. This is set up right now so that all the lines that are on are on, okay? And notice, by the way, I'm going cold pad. I'm doing better actually. I gotta, my apologies. Uh, Sorry for any children in the room. I'm making myself comfy with a couple of cold packs because I'm not quite there yet. By the way, during the daytime hours, I only take Tylenol PM, just so you know. I'm not currently in a narcotically induced state. Okay, notice that if you look at these circuits, all these lines are just kind of like, we don't know what they are yet, right? They're just kind of dead. But notice that where the one is right here, that is a kind of a thick red. You see it, a little thick red line coming out of every one of these bits that has a one. You can see them. And when there's a zero, those lines are all dead. Okay. Now we're reading a value, which means we are going to try to get these lines down here, D2, D1, D0. We're going to try to get these lines to contain the value at location 1, 0, which is going to be, you know, this one right here. Literally 0, 1, 2, address 2. Okay, that's what we're doing. They're going to show up down here. So what are we going to do? What just happened there? What just happened there? Oh yeah, okay, I went the wrong way. Wait there. I'm like, okay, what animated? What animated? Okay, over here, look over here on the address line. We're going to drop the address in now, okay? We're going to make the address line go live and be what it's supposed to be. The address is 1, 0. So the first line, 1, 0. So what's going to happen? It's going to hit here. That's going to, let me see, that guy's not going to work. This AND gate is not going to work because the one's going to get knotted, right? A 0 in an AND gate blows it up. Any 0 in an AND gate just goes, nothing's coming out of this thing. One line has veto power in an AND gate. But here you're like, oh, the 0 gets to the knot and the 1 gets on through. This guy's going to go live. That guy's going to go live. You can see it. So boom, there you go. Now that guy goes to big red, right? Big red lines. See it? See how the lines go? Now notice something. Notice something that just happened as soon as I did that. I just activated these lines right here. You see it where my cursor's moving? Right there, I've got 2 1s coming into an AND gate. 2 1s coming into an AND gate, and again, 2 1s coming into an AND gate. What's coming out of that AND gate? You know, you already know, a 1. So that line comes ripping down here into this OR gate. Now that OR gate's going to turn into a 1 as long as any of these are on. It's going to be a 1. So it turns on and it flips through. And there we go. Those values are now in these lines. So we now have lines coming out of these registers, these memory locations with the values there. You know, it's on. Okay, that's it. That's reading from memory. Cool. I'm going to move. That one's kind of the easier one because we didn't do anything to the values in memory. We just took them and we just perceived them, right? And just understand that all these values all the time are just sitting there ready to go. Like that guy's sitting there ready to go, but nobody, you know what I mean? Phone never rang. There was no date. There was nobody's, you know, Lonely Hearts Club over here. And same here. He's just sitting there, but nothing happened. Why? Look at the line. That's the address line coming in here on the address line. And so the address line, because this is a decoder, one of these is going to turn on. And when that happens, it's going to enable, it's kind of like a big Rube Goldberg machine, right? It's like, remember Mousetrap? Remember the game Mousetrap? Which was, it turns out, when I played it as an adult, it wasn't nearly as incredible as I thought it was when I was like 7. Anybody else have that horrible soul-crushing disappointment to play Mousetrap when you're an adult, and you're just like,
I haven't played Mousetrap in years or thought of it about it in years, but I'm picturing it now.
yeah, no, it was not as impressive going back to it. But you see what I mean? Why I'm calling it like a? They call these Rube Goldberg machines. There was a, I think the guy's actual name was Rube Goldberg, who would make these elaborate long ago. You can look that up, and if somebody wants to drop a link to like a Wikipedia article on Rube Goldberg, that would be fantastic. But they became known as Rube Goldberg machines. You know what I mean? The elaborate, this flips this, and it just keeps kind of like daisy chaining through whatever. Um, and oh my gosh, there's a band. What's the band? Somebody tell me. There's a band that does music videos that are basically Rube Goldberg machines. I want to say Go. Is that ringing a bell?
It's okay,
Okay,
go.
Go. Okay, Go. If somebody would like to drop a link to, there we go. There we go. Thank you. There's Rube Goldberg. Oh, awesome. Thank you, Matthew. The self-operating napkin, right? Um, but the classic, there we go. Thank you, Eddie, for the Wikipedia article. Somebody want to drop an OK Go video one? If you're a fan, I'm a fan. I just have only been exposed to them like in the last year and not prior. So I didn't have a lot of exposure. Okay, boom. Yes, that's a classic. Oh, with the Rube, and it actually says, "Okay, Go. This too shall pass." Rube Goldberg machine official video. Uh, I know there's a strong temptation to watch that right now, and I'm not gonna blame you if you do. We're gonna keep talking about this, but I really recommend you watch it. But I'm just saying that if you understand that that's all we're doing here, instead of being like, "Oh, it's so magical," no, 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 no. It's just like water pipes. I got water pipes going here, but it's the spigot's turned off. Is it spigot or spigot? I think it's spigot, but that my cultural
Yeah,
upbringing taught me spigot. I think it's like a Midwest accent to say spigot. I feel embarrassed now about my cultural roots as a Midwestern boy, growing up saying spigot. Sorry, I'm having an existential crisis right this moment, but I'm going to be back real quick. Spigot, spigot. No, right? It's just like a valve. It's a valve. The AND gate is just a valve. It's off until it's on. And to turn on, all the pipes coming into it have to have stuff coming in. Then you can go joink and then the water will flow. If you just think of this like a big Rube Goldberg machine and try to understand it from that perspective, uh, I think it's a little less like crazy mysterious because electrical current, actually works a bit like water, works a bit like water flow, and you can conceptualize it like water flow. That's why when this line comes in and turns on this, and then that guy, all that line, these lines turn on, when that hits this, that valve switches, now the power can run. It gets to this guy, which has always just been waiting to take anything coming. And if anything's on, it'll kick out a signal. And boom, 111. And we could do the same thing with any one of these, and you should do it yourself. Maybe even like print one of these out and take a marker even and just go like, okay, these go on. You know what I'm trying to say? Then these go on and just do it manually. And then you're like, okay, I got it. I figured it out. You don't have to build one of these. You don't have to come up with this. You just have to understand it. Okay? All right. I think anytime you can lecture in computer science and talk about Rube Goldberg, I think it's probably been a good lecture. I think there's some achievement level has been unlocked if you can pull that off. That's my kind of personal philosophy about that. But yeah, Rube Goldberg forever attached to this idea of these kinds of crazy machines. Okay, now we're going to write it. You ready? We're going to write a value. So, but we're going to, just to keep it simple, we're going to stay with the same location, okay? Same location. Location 10. We can also call it number 2 if we feel like it, right? 0, 1, 2. But it's location 10. And then this line here tells us, right? 1, 0, like these are the values of the line. And we're going to write the value to that 3-bit memory location, okay? And we're back to where we were before. These are still kind of like, you know, dumping out here to the AND gates and everything. Okay, what did I just do? What was the animation? Hang on. Oh, there was no animation yet. Okay. I'm going to put 0, 0, and 1 in the data right up here. Okay. Where's that coming from? We don't know and we don't care. It's coming from somebody else is controlling that. And really, we truly don't care because somebody else kind of owns it. All we need to know in the memory is that we're just going to run with whatever the values are on the data lines coming in. That's it. How they got there, whether they're correct, we don't think about that. We don't care about it. 0, 0, 1. So you see what happens here now. The 1, here comes the line. It hits there. It hits there. There, 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 there. Okay? Now, what is that doing? The next thing we do, we have to select the address. So we do the same thing we did before. There's 1, 0, right? Which when it gets to here, that guy's coming on. Okay? So once again, by the way, all these lines coming down and out, like these data lines down below, they're going to get messed up right now. Just FYI, right? You see how this AND gate now has stuff flowing? It's coming out. That D is going to turn into a 1, but we don't care. We literally, in the same way that when we were reading value out into those data lines, we weren't even looking at what was up top. Same thing here when we got stuff up top that we're trying to put in, the artifacts of what's popping out down below, don't care. We're ignoring it. We're not looking at that at all. Doesn't matter what it does. We literally just ignore it. Okay. Now, as a byproduct of that ignoring, I want to just point out to you that the fact that these lines are going to go red and that's going to turn into 1, I didn't even put it in the animation because I don't care. We don't care. So I'm not putting it there because I don't want to focus on it, but it's there. But notice these guys are on right now, okay? All right. And the address line has been selected. Now notice, let's see. Oh, here's the critical thing that this address line has done. Over here, this is what we were doing, you know, where it joins this AND gate and dumps out the bottom. That's for reading, and we're not reading right now. So that's just really, all of that's wasted. We don't care. The only thing that line is doing that we care about is right here. It's turning on that AND gate for everybody, by the way. Well, sorry. It's going to turn on that AND gate because this AND gate went live, right? When that line went live, this AND gate went live. That guy stays dead. That guy stays dead, dead. That guy's live. Okay? Now, what is that guy connected to? Back it up. Follow the line. That little dot, by the way, is like a kind of a connection joint. It connects. It's all part of the same flow. What is it? Our old buddy write enable. Remember write enable? Remember that when we got the whole thing set up and we go, and then we wait for a second and we're like, and then doing that caused the value to latch in. There it is. That's write enable. And as soon as we have that guy ready to go, we're now ready to go. Okay, hit the write enable. We hit write enable. Notice that write enable hits the entire memory. It hits every one of these in the whole memory. But because the address is not selected, nothing happens. Nothing's there. Nothing's there. Down here, nope. But here, because that address was selected, the write enable gets through. You're tracking? Because the address was selected, then the write enable can actually penetrate and get in here. All right, so there we go. Now you've got an AND gate with 2 lines coming live. That guy's got to go live. Boom, he goes live. Okay, now you just turned the write enable on inside that latch, okay? And we also did this thing for all of the values, every bit in the byte concurrently. in parallel. They all happen at the same time. Like going, like boom, boom, boom. All three of these are going. Okay. Now, the other thing that's happening is there's the data line, that 0. He's showing up right there as a 0. See that line, there's zeros. That line and that line are zeros. And these guys here are 1. In other words, if you remember, because I know you don't, but if you did, if you remember the RS latch, right? That when you were a 0, it was going to cause the value of that latch to turn into a 0, and which was reset. And if it was an S, if it was a 1, sorry, that was going to set it, and the value was going to turn into a 1. Remember this? But it was waiting for the write enable to go, okay? And to make that sound. All right, so as soon as I do the write enable, these guys change. That 0 gets latched in. The 0 latched in. That guy was already a 1, but it's okay. The 1 latches in again. Then what do? The write enable's down. Now we release it, right? Write enable now comes up. Those values are now in memory. And Junlin, my little mouse is so hard to see. It's true. It's true. I'm sorry. I need a better solution to that. In fact, in the not too distant future, I'm going to buy myself a Windows machine specifically for these kinds of broadcasts, a PowerBook. I think there's probably a few more tools for Windows that might give me a little bit of an ability to, I'm not sure, touch screen, something that'll give me a better ability to gesture in the context of this of the screen. Anyway, that is reading and writing to memory. We did a dinky little example of a 12-bit memory, 4 bytes, 3 bits each. Yeah, so then what happens? Yeah, then we just like turn the address back off. The lines go to 0. They go back to just kind of like laying there, doing nothing. That's it. That's it. Any questions? Yeah, Gabe, this is how you set and retrieve memory. This is how you write to memory. This is how you read from memory. Yep. And who said it? Who said it Tuesday? It's just a hell of a lot of work. You know what I mean? Like this is like a crap ton of work to just, put a 1 somewhere in memory and then recognize that when you've got a gig of memory that you're doing this freaking billion, you have a billion of these lines, and you're like, wait, that line literally like lights up a billion lines. Yes. Now there may be technologies that are current cutting edge that the EEs and the computer engineers, but I think that's mostly an electrical engineering thing. You know what I mean? That I don't even know about, that I won't know about because but this is the foundation. This is the fundamental. Yeah, Matthew, if you wanted an 8-bit byte, you just add 8 more to the right. Yep. You just spread it out. And then you'd have, D, you'd have, D0, D1, D2, D3, D4, D5, D6, D7 along the top and the bottom. Yeah, man. Isn't that cool though, really? I mean, again, it's a Rube Goldberg machine that's really clever. There are actually, if you look at this, and I know it's intimidating, but there are, in fact, not that many moving parts here, really. There are not that many actual moving parts. You have to just take the cleansing breath and let the intimidation just kind of like subside. Thank you. You got to let that just kind of like calm and then just be like, okay, let's take a look at this thing. Let's take this one step at a time. Okay, so how does it not read when you're doing write enable? Yeah, and the answer to that one, Matthew, is those values at the bottom, the same control structures that put the values in the top, that made sure those lines had the right values so that it could latch it in. That same structure sees that, is aware maybe, or maybe it doesn't even care. that the lines at the bottom are actually changing their values, but those lines are going into something, probably an AND gate somewhere, or some multiplexer or some other device that just is set to ignore them. So they're changing here, but in terms of the rest of the computer, the rest of the system, it just gets ignored. Nobody cares. And yes, that's the bottom line. Does it not matter that it can read while write enable is being used? No one's reading it. There's like someone's down there screaming at the bottom, but nobody's listening. You know, that's the bottom line. Everything else coming out the bottom while you're writing is going to like some, valve that's turned off. Nobody cares. There's nothing turned on to look at you. So you can change and flip and do whatever you want. Nobody cares. Yeah. Yeah. So yeah, Gabe quoting Junlin, I'm very suspicious of the fact that I'm understanding. Yeah, I'm with you on that, honestly. And the other thing too is, talking again about this theory of learning, there is a danger sometimes that in this moment there's some clarity because Dr. K is talking or whatever. Then there's a moment where you're like, I really understood today. And then you have this alone moment and you're like back to existential crisis, where you hit it yourself later and you're like, ah, and all the voices start screaming. Um, you know, that's the thing. But if you understood it once, you got to go back. You just got to go back through it again, 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 and let the homework be your guide as well for all the things. Okay. All right. I'm going to keep going because we got to talk about sequential logic circuits next. We're almost out of this, by the way. We're going to finish this today. I believe it. I believe. Okay. We've talked about two different kinds of circuits. Hospital drinking mechanism, still cool. Okay.
Somebody asked a question.
Oh, hang on, I missed it. Hold tight.
Well, they said it on the thing, but I guess you didn't hear them.
Oh, I didn't know.
They asked when are we going to turn in module 4? When is that going to be due?
That'll be due. This is module 4 stuff, right? See, I was going through, revving from the old lectures into the modules. I think, and is Walter on? If Walter's on, I think that Walter not on, Zach not on. I feel so alone. No, I think that module 4 is the one we're on right now, right? Which is all this kind of stuff. Is that correct?
Yeah.
You're like, wait, you should know this, Dr. K. Yeah, Dr. K has been unconscious for a month. So I'm coming out of this thing.
Yeah, so we're on module 4.
Yeah.
And
we always go, don't we always have the thing due? Again, I've been unconscious for a month. I think we always do, is it 2 days that we've been doing it? Like once we finish it, then the module homework is due like 2 days after that.
So then Saturday?
Yep. And again,
cool.
And Eddie, that it's an encouragement deadline. You don't lose. There's no loss of points. There's no, you know what I mean? But it does turn into a 0, so your grade reflects it now to remind you, even though you can, you know what I mean, hit it whenever you can. And then ideally, my cool ideal is, you've been playing bingo the whole time. And on a day like today, you would like wrap up the homework and submit it like today, that would be ideal. But yep. Well, that'll all be due. The official due date for module homework and exam will be Saturday. Rock and roll. Okay. And yeah, Eddie, I really didn't hear the audio on that question. I'm not sure why.
Who is the one that asked the question? Because maybe you have them muted.
I might have them.
You.
I only have one forced mute, which I'm going to unmute right now. It was just somebody that sometime or another
had a hot mic.
Had a hot mic that they were not controlling. Exactly. I am unmuting the one person that I had muted. And it would be hilarious if they still had the hot mic going down.
That was me,
Was
but
that No, it wasn't. It wasn't. It was somebody else that I had muted.
no.
Somebody who's
We're
been
good.
silent.
We're good. I think we're all good now. We know what the due date's going to be.
Yeah.
We can move on to sequential logic circuit.
We shall move on to sequential logic circuits. Here's the deal. We talked about combinational. These are like a lot of big words, right? It sounds like, what'd you learn today? Combinatorics, and you feel like you have like all these big words or whatever. Combinational logic, all that just means is like combinations of stuff. And we just figured out like, combinational logic circuits is basically says, what is the line doing like right now? If both of those lines are on, then what's coming out is on. And it's just like, what is right now? If I power the whole thing down, it doesn't matter or whatever. This is all the simple gates. It's also the multiplexers, decoders, adders, right? And then but you can't store information in those. And then we use that with the cool RS latch and the D latch to make memory circuits where you can store information. So you have these sort of like behavioral circuits that are just like living in the moment. And then we have memory circuits that are just kind of living in the past. And what a sequential logic circuit does is kind of brings those together, because sequential just means I actually can do things where there's sequences of operations. You do this, and then this happens, and then this happens, and this happens. Do you see my impersonation of a sequential logic circuit? That's freaking genius. That's all I got. All I got. Okay. So let's talk a little bit about combination versus sequential. Look at these locks. You know these locks. You've seen both of these. What's the difference? They're both combination locks, right? You have to know the combination. Isn't that what they say? Like, you know the combination to the padlock? Or I can't remember the combination. That's the terminology, right? What's the difference between these two? Talk to me. This is class participation time. This slide is an exercise to the student. Yeah, go.
Yeah, so on the one on the left, it's more you just, you input them in a row and you see them and then it opens.
Okay.
Whereas the other one, you have to know not only the code, but how the correct way to spin it, and it's the actual act of spinning it to the right points that opens it rather than just inputting the numbers.
Okay, that's a lot of good. I like that. Gabe. There's a few more things. Junlin said one is 4 numbers, the other one is 3. Correct. Also true. That's not.
I think one of them is you can't go back and switch the first number after you've already set it for on the second one.
Yeah. So right. Who said it? Gomez. How else can you explain that? I think you're onto it. All of these are true, by the way. All of these are good, but working towards something important.
One of them is like, it's not just the right numbers, but you need the right sequence, and you can't go back.
Yep. Combination versus sequential. It's order. It's the order, right? The one on the left, does it matter what order? You're right. I can spin any of them into the correct position as long as at the end of the day they're all okay, right? If they're all what they're supposed to be, the lock will open, right? I can do the first one first or the fourth one first, right? Order doesn't matter. On that combo lock on the right, it's sequential. The order matters. I got to spin it, and then everybody, like I said, everybody was saying correct things that we're building to this sort of idea, but I have to like spin it to the right to clear it, right? And then I have to like go, okay, go to the right to a certain number. Then having hit that number, I then have to go left past the number, the target number, and then back around to it, and then to the right back to the third number. That sequence, that order is important. If I do the same three numbers, but I flip the order, it's not going to open. As you know, in contrast to this lock on the left, where if I do it in this order or do it in that order, it's still going to open. So order, order. And what this actually introduces us to is the idea of state information, okay? State. We already talked about the order in which the unit numbers doesn't matter. There's no information about state, and I want to introduce this idea of state information, okay? And we're going to introduce you to the idea of a state machine, which, by the way, turns out to be a very, very critical, essential to the field of computer science, as it has been, you know, constituted for most of the last century, unless something changes, you know, at some point in the future. State machine, state information becomes very, very important in the field of computer science. Also, you're going to hit it again in other courses, and there are some courses where you're going to dive in very, very deep, where you talk about finite state automata, automata theory, and other kinds of stuff that's going to deepen your foundation in the theory of computer science. Okay, so here's what a finite state machine is. Now, let me just talk for a second about states. What am I talking about? We're not talking about states of the union, the state of the union. We're talking about state. What are some other words that have similar linguistic roots? Status, right? What's the status? That's like a Latin version of state. What are some other? I think that's probably the best one. Status. What it means is that you have the ability to look at the world, look at things around you, and conceptualize them as moving through different stages or states. For example, right now we could say that we are in the state of being in class for CS 2810, right? There's like, I can move to like prepping for class state. That prepping for class state might have some other substates, like getting my streaming stuff up, get the YouTube going, right? Some of that kind of stuff. But you can talk about you're asleep. For some of you, that's right now. You're then, whatever, your alarm goes off, there's a trigger, you wake up. There's a state of getting ready for your day, whatever that looks like, eating your breakfast, doing your whatever. And then there's a state of like doing your homework, right? We move through, you can deal with it at a very, very fine-grained level, or at a really macro level, right? You guys are mostly young adults, mostly young adults. I am mostly an old man, an old decrepit man who is going to go to Cabela's today and buy a cane. This is what I have been reduced to. Okay, but these are states of life, right? There's like, you're a toddler, you're a newborn, right? You're so cute, and you're a little rugrat, and then you're a toddler, and you're terrible too, and etc., right? And you're a little kid, there's like, you move through that's very linear, but you do move through these states. The reason that the overrated, not that great a movie, Benjamin Button, was kind of clever was because he's born as an old man, right? And he ends his life as a baby. Well, the states are out of order. That's why that's clever, because the states are out of order. Okay. But it's still like, that's pretty linear, so it's boring from a state perspective. Okay. So what we're talking about, tell me, Matthew, about position works 2 for state. What do you mean? Just I'm not sure if I understand your question. as drawing upon the same root? Is that true?
Well, similar enough that it could work.
Maybe. You got to get down
for
to the sort of, the etymological roots of position. I don't know. I truly don't know. Yeah. Mode, I think, is also similar in meaning. Yeah. So let's talk about states. And we're going to draw some pictures, so you'll get a feel for it. But there are these various states. There are inputs that take you into the state. Like, for example, there's a state of applying to be a student at UVU, right? Then they send you a letter or an email or whatever, and it just says, congratulations, whatever, blah, blah, blah. You're now officially an accepted student. So you move into the state of being an accepted student, right? And the input from that is there's something that you can have input, that's happening while you're in a state. You can also have outputs that are happening when you're in a state. There's behavior in each state, and then there are transitions between those states. So I transition from applying to accepted to like enrolled and registered and actually attending, right? I mean, there are distinct states that you move through. And it turns out that in building software and understanding the world, in order to build software, a lot of the world is modeled very, very readily via state machines. Not just how do I want to build my software, but a lot of times software has to mimic a little bit or copy, right, the world, because it's going to describe the world or interface with the world or help you manage the world, right? Software has to, in fact, I want to just say this too. Some of you are questioning whether you want to be a CS major, and some of you are like, I don't know if I want to code all day. You can be a CS major and not have coding all day for your entire career be your destiny. Just want to say that. Those are not hand in hand. Can be, often is, doesn't have to be. And why did I say that? Because computer science, one of the things that the field of computer science does, I think it helps you to like understand the world. I really do. Because all of CS either models the world or interfaces with the world, right? At some level. So all the core structures, as you look at them, object-oriented stuff for programming, the various programming paradigms, whatever. All the things in software have some real-world analogy that I feel like it just gives you skills to analyze the world around you. And I love, love, love that part of computer science. All right. Yeah, you can edit. Yeah, there's even more than that, it turns out. Okay. All right. So here we go. Finite state machine. And by the way, I want you to just noodle for a second. We'll have a minute. I want to just see, as you can noodle, or maybe even just drop them in the comments, examples you can think of that really clearly, like systems like this, that you can just think about in the world, that you would have to look at and just go, that really does embody a state machine. I'm not even just saying you can use a state machine to model it, which is true. I'm saying the machine itself implements a state machine. Just like that spinning combo lock, the sequential lock. Okay, just like that. That lock implements a state machine. It's not just that I can describe it with a state machine. It implements a state machine. Okay. Traffic lights, what do you think? There are 3 states, right? Green light, yellow light, red light. We're ignoring more complex traffic lights with turn signals and, various things. We're ignoring that. And we're ignoring like the flashing yellow for yield, and we're ignoring more, there's other behaviors that we understand. But just take the classic traffic light, green, yellow, red, that's it, right? And there's a behavior, or in other words, an output that happens when you're in each state. What is it? Well, when you're in the green light state, the green light's on. That's it. And then the others are off. That's the behavior. And when you're in the red light state, the red light's on. Crazy. And there are triggers, right, for transitioning between the states. Interesting. Matthew mentioned trees have different states depending on the season. Agreed. Yeah. What's the trigger on a traffic light? The classic, old, traditional, stupid traffic light. What was the trigger that would cause a transition? What say you? Yeah, gave a clock, right? I mean, some timer, right? So much time here, right? And then in the classic world, it would have to cycle through, even when there was like a left turn lane, right? You'd be like 3 in the morning at an empty intersection, right? And it would just like you watch it go, da, 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 and yours is coming. Then you get into ones where it was like, it had like sensors as the trigger. But if you missed the sensor somehow, you sit there forever, kind of thing. It actually happened to my dad once. It was literally the middle of the night, and he's sitting at this traffic light, the city, and there's nobody anywhere, and the light's just sitting there, and nothing's changing. He sat there for like 3 minutes. Finally, he just like, I'm just going. So then he just goes, through the red light, and then literally it's like, boo! There's like a cop right there, pulls him over. Look, we are the only 2 people awake in this city. I think he talked him out of it, but right. Oh, and Matthew, yeah, they can be overwritten to clear traffic for police or fire. Right. Dandelions, the yellow state. Oh, the yellow state. Right. Yes, the beautiful yellow state, and then the fluffy, we shall spread like the plague state. Right? Both of which are by the way, charming to children who will take the yellow ones and be like, and whatever, and they're beautiful. And then when they're, this nimbus, then they're like, look at me, I'm spreading weeds. Anyway, yeah. Anyway, you get the idea, right? This is not really hard. This isn't hard. This is pretty straightforward. And by the way, keep dumping. Junlin, do you want to edit? I think you started there, and either I don't understand what you said, or edit that bad boy right there. Here we go. There's the we can draw the finite. Here's how we draw finite state machine. We always put the states in some kind of circle, box, round, usually rounded. Okay. And then literally in the old dumb classic, the red timer expires and we transition to green. And then the green timer expires and we transition to yellow. And the yellow timer is, yeah, it's pretty straightforward. Right? Not hard. I'm sorry, Chun. I don't know the trick of using yellow dandelions to pretend that your friends got peed on. This must have happened generationally after my childhood. So, and you can drop that in the comments. I'm dying to find out. Oh, you rub it on the arm, it leaves a yellow streak. Okay, so Junlin's childhood is dandelions as a weapon of violence of some form. Okay, let's keep rolling. How about this one? How about that? Anybody ever seen these? We don't have these a lot in Utah. If you're in a larger city, or you lived in a big city, or traveled to a big city, or been to, I don't know, where do you see these? Amusement parks. Even in Utah, we got Lagoon or whatever, right? There are these things, right? But these can be more complex. But if this is like a subway, and this does look,
turnstiles.
yeah, the turnstiles, and this I think is a subway. And basically we can model this system as simple as like two states. It's locked and it's unlocked. Ta-da, right? But what's the triggers, right? What's the behavior? When it's locked, the behavior is to just be locked. When it's unlocked, the behavior is to yield to pressure if somebody pushes against it, which moves it to the locked state, right? So actually, let's check it out. There we go. When you're in the locked state and there's like payment received somehow, you drop the money, swipe your card. You know, these are different all over the world. You have your little ticket, you put it in the front, you keep walking, you put it in, you go through, and then you pick it up on the other side as you're leaving. You know, there's a lot of different ways of looking at that. And then when the payment is received, it unlocks it, and you're now in the unlocked state. When the turnstile is rotated, then it returns it to the locked state. Again, do you see what I'm saying? I'm just trying to say that a finite state machine is a theoretical construct, but it gets really handy to build software. Whenever you're building software that looks like that or acts like that, it's really, really handy. And here's a true story. My first job out of college, I did a lot of stuff in college, including building software and doing some startups and stuff. This was in the 80s. The 1980s. Um, when music died. Sorry, 80s music fans. No, there's some great music in the 80s, but anyway, the 80s were a dark period for me when it came to music. Where am I going with this? I graduate. I go to HP in the Bay Area. So I'm in Sunnyvale is where that HP facility was at, and I'm building device drivers for the original Hewlett Packard personal computer, the Vectra. We called it the Vectra Classic. American Pie. I only saw the thumb at the bottom. Don McLean, The Day the Music Died. Yeah, that's a classic tune. Classic tune. I'm writing a keyboard driver for the operating system is OS2, and the platform is the Vectra Classic, the original HP personal computer. And I have to write this device driver. I'm modeling it on the DOS device driver and or the BIOS code that shipped in the hardware, but the BIOS code wasn't reentrant. So we had to rewrite all the drivers for OS2 in the form of device drivers. And I was doing this. And keep in mind that I'd gone through my entire undergrad at Iowa and BYU, right? Those were my undergrad schools. And I'd been exposed to state machines, and somehow, I don't know, it's like I did all the homework, but it never really clicked, like why I should frickin' care. It never penetrated for some reason. I don't know if professors said it and I missed it, or if they never said it. I truly don't know. But I do know that I got there and I'm like, I got to build a device driver. And I was also fresh out of college, and they're giving me like code to write, new code, brand new code to write. Like, whoa, okay. And so I start diving into this thing. I'm like, how am I going to do it? And then I realize that the function of a keyboard in the context of a personal computer is that of a state machine. It all operates I could build the entire thing as a state machine. And in fact, that's what I did. And then I learned later that the state machine was a classic way of managing keyboard input. But I just kind of like noodled on it. And then I built my entire keyboard driver around a state machine idea. And then it was just like, oh, my gosh. And I finally understood, I guess, at some level, why that sort of mattered, right? And I can get into it later. It's a little more involved to talk about. But you think about the fact that, all right, if I press a key, is my caps lock key on? If my caps lock key is on, then I am in a certain state, am I not? The state of, relative to the keyboard. If I press the caps lock, I am in the state of all letters are capital. And if I undo that, I'm at least in the caps lock state, right? If I press a shift key, of which there are two, either one of the shift keys or both, I'm in the shift key state. And if I'm in either the shift key state or the caps lock state or both, I am in, I'm going to treat the character that I'm pulling out of the keyboard differently. So that notion of this of state. How about this one? You press a key down and you press skip. Turns out that on the classic PC design, there were scan codes that were generated. It didn't send you the character from the keyboard. It sent you a code, a value, some hex value. And the hex value, but it would send you a certain value when a key went down, and it would send you another value when the key went back up. Down, up. Why? Because if I go down and hold it down, that would trigger what we call this typomatic thing, where it'd be like, and it takes off and repeats. How, why, well, what? The reason is because I can detect that it went down, start a timer, and at a certain level of time, it's like, he wants to repeat. And you start just repeating that character, right? Typomatic rate. That only works if I can detect that I am in a state of this one guy goes down, this guy goes up, etc. Anyway, there's a lot of things that can be built around that kind of state machine. And by the way, you're in luck because there's a simulator. We're going to get into Lc3 fairly soon. Okay. In fact, we're going to give you your first look at the Lc3 architecture in about 10 minutes, 7 minutes. And there's a simulator built by, I can't remember his name. Really grateful to this guy for doing it. It's really useful. It's very well done. It's open source. And we have taken that source and are making some changes to the code in order to allow you to do a better bit of work relative to state machines and having it be kind of native. I'm going to change some of the stuff that's in the assignments down the stretch so that you can actually implement a state machine in assembly language. And I'll show you how to do it. And I think you're going to find it very, very cool. And it just opens up a lot of things. When we get to the large project, if you can implement that as a state machine, so much easier conceptually than almost any other possible way of looking at it. And we're going to walk through all that. Okay, so we're coming back. State machines are coming back. Now, all right, so what about the state machine for this combo lock? Well, if we were on the board, we could go through this. I'm not going to belabor because I think we've done pretty well. But the bottom line is, and I don't even have the things. What we've done in the past is just gone to the whiteboard, when we're in person, like we hopefully will be in the fall. But bottom line is that A, B, and C are locked states and D is the unlocked state. Bottom line is you're in state A, which is like the whatever you found it state, and you spin whatever, but you stay in the A state until you hit the right number. So what was the combo? R13. You move to the right till you hit 13. And when you stop and start going left, you now have moved to the B state, right? And you go left to past 22 to 22 again. Now, if you keep going, right, you're going back to state A. But you're following me, right? When I go left to 22, when I pause, and as soon as I start to go right, I'm now in state C, right? So we can logically talk about break that down into a lot of detail. This graph can kind of complex. And then again, we're going to go right to 3. And when we go right to 3 and stop, we are in the unlocked state. If we pause and go back left, we back to A. If at any point we go, back to A. Okay. Cool. Here's just some examples of real. I did a little looking online for people that had done their own state machines. Here's one for, I don't know, LED is blinking, LED is on, LED is off, press the button. You know, you see again, there's certain formats, there's nothing magic. There's no one true standard for how to draw it. There is UML, which is kind of a bit of a standard of sorts, but it's not required, mandatory. Okay, what about that one? Here's a moderately sized one, which is a little intimidating, right? But if you look at it, it's actually still, it's just trying to describe these movements between these various states, okay? And this happens to be a call initiated with like a Bluetooth connection or something. I'm not sure exactly. Okay, what about this one? This one is the actual state machine for the Lc3, which is the mocked up processor that we're going to use for the class. We're going to actually come back to this graphic because this goes through the fetch, decode, execute cycle of grabbing instructions from memory, decoding them, and executing them. And all of this is just breaking down all the places. Remember I said who's controlling it? There's a control unit that's running as a state machine inside the Lc3. That's what's making all the decisions. But just to show you that we did the traffic light, the turnstiles, very simple. They can get much more complex, okay? All right. And the last thing I want to talk about, because we're almost out of time, is just this idea of a clock. The clock becomes very important in terms of circuitry. Sometimes we have to have timing. Well, you've got to have a clock in order to have timing. How do we get a clock? Well, we actually have these, they make these clock chips for computers, and they're made out of crystals that have a known oscillation. And based upon that known precise oscillation of the crystal, they can be like signal, signal, signal. I don't know how you build those circuits to make that happen. To me, solid magic. Solid magic. But a clock circuit is simply a signal that alternates between 0 and 1. It's like I'm off, I'm on, I'm off, I'm on. It just does this on an absolutely precise timing. Okay, it has to be absolutely precise. And the bottom line is, think of it this way, kind of like the Rube Goldberg thing again. It's like when it goes to 1, the whole machine just goes and moves like 1 step and then pauses because it goes down. It goes on, like when you do the right enable, and I was describing like, then you wait a little bit, then you go, you undo it. Well, that's the clock. The clock's gonna, the system as the clock goes on, it's like the right enable goes there. And then it's like clock goes off. Clock goes on, and maybe it waits again. And clock goes off. Clock goes on, and then it releases the right enable. There's timing known to the way the system is built to perform these various instructions in the hardware. The concept is really important. So it literally just looks like that, where there's a clock cycle. That is 1 on and 1 off. That's the clock cycle. This might be the end. No. Oh, here's another example, which I'm not going to go through. This one, honestly, at a certain level, is maybe even more confusing than it needs to be and might be worse. Okay, I said 7 minutes. It has, in fact, been 7 minutes. Exactly. And we have a minute or two. Once again, this is a big, ugly freaking diagram. This is going to become happy second nature to you. You're gonna be fine. You're gonna get it. But this is, and that says the data path of the Lc3. I just want to introduce you to this idea that is the architecture of the Lc3 computer. And there's one feature that I want you to just be aware of for now, and we will break all the rest of it down. Notice right here, finite state machine. That is the state machine that is running the entire system. Notice memory out here. That's the memory, like the one we built. Registers, remember the registers we built? The ALU is an arithmetic, also called an arithmetic logic unit. That's where the adder lives. Adding, subtracting, doing multiplication, division. That's all in this ALU. And the rest of it, we'll break down. We're gonna get into it. But the feature I want you to think about right now is, yeah. Let's keep Einstein a little bit calm there, right? See the big thick arrow, right? That guy right there. That is called a bus. It is also called the data bus, and it's actually just a thick bunch of lines. You know, could be 16, could be 8, could be 64. You know, it's a bunch of lines. But from our perspective, we can just conceptualize it. It's literally called a bus. It's a weird name. I sometimes just think of it as like, you know, the campus bus, you know, these campus buses that are like free or whatever, and they like take you over to the different campuses, you know what I mean? And they move, and you can ride the buses, and they just kind of go in a circle or whatever. It's actually kind of like that, you know? So whenever data has to move around, it gets put on the bus, and then then the bus like moves around. I'm literally and figuratively hand waving here. And then it can kind of come off of the bus. So when I got to send stuff to memory, like to write to memory or to read from memory, like we were doing, right? Remember somebody like, what about the reading? What about the reading? Well, when I'm writing to memory, which is this operation right here on the right side of memory, sorry, it's actually both coming in this way. When I'm writing to memory, the lines are all set up so that whatever's being read doesn't matter. That's all happening right over here. But I can put stuff on the bus and then instruct the memory to pull it off. We're gonna come back to this over and over and over again from now to the end of time, yes, and of this class. And believe it or not, yeah, frick, man, it actually happens that I do, in fact, that was a long one. That's a long one. That was 4 class periods, solid, to deal with just all of that material. It's a lot of material, but you just gotta dive in, spend the time you need to get your head around it, and check in with me and Zach and Walter, you know, to get extra help, you know. So that's it. Spring break. Thank you for spring break. And I'm gonna just be here with Hubert. We're gonna be hanging out. Okay, where am I at? Oh, yeah, there we go. Me and Hubert are just gonna chill and try to catch up and get my back healed and my stupid nerve pain taken care of. So there we go. We'll let Hubert just kind of like take us home here. So that's all I got. When we return, I think I'm going to be like a new man. I'm going to be like a whole human when we get back.
When we return, we'll see him as a human. Sorry.
Wait. What?
Sorry. It sounded like when we return with our next episode, you know, like, this man will be new.
This man will be a whole human. Yeah.
He will be functional.
He will be less dependent upon his plaid monkey for emotional support. This is, by the way, my emotional support plaid monkey, and he does live on my desk. And he's
adorable.
He is crazy adorable, isn't he?
I would love to wake up to that face every morning.
I know, right? He is the cutest.
Hey,
Next
Dr. K.
time on CS 2810.
His name is Hubert.
I'm gonna go now because I'm really tired,
Get
obviously.
out, Eddie, go take a nap, okay? I'm gonna do the same. I'm gonna do the same. See you, everybody.
Really quick question.
Yeah,
On
Texas, go.
that last diagram that you showed, is that a very similar concept as like how data gets pulled from the hard drive, goes through the CPU, and then gets put onto the RAM,
Yep.
and then vice versa?
Yep. Absolutely.
Okay.
Absolutely. That data bus is literally, that is the data bus. That, like, you know, in the old, I have not like broken apart I've been doing MacBook PowerBooks, you know, for the last like 15 years. So I haven't even had like a Windows Tower desktop, whatever, like with a box. But the classic, I don't know if they're still like this, but the classic was you had these like expansion slots and you put a card in there, right? Well, that
Right.
expansion slot is literally an extension of the bus. That's literally the data bus coming up to like greet you, and then the little gold, you know, surfaces, right, that you plug in. Literally,
Right.
it's like bit, like patch you in and connect you into the bus. Absolutely.
Oh, okay. Cool.
Right? And that's how
Right.
stuff moves. Now that's how you get into, you know, in and out. And so the CPU can just deal with all the crap, peripherals and all the other junk.
Gotcha.
Yeah, man, great question.
That's really cool.
Yeah.
Well, thanks, Dr. K.
All righty. Okay, take care, everybody.
Bye.
See ya.